Hi everyone, welcome to Math Spellbook. I'm your host Peter, and basically we are going to get into the rational numbers today with Sascha. So I will call upon Sascha to join us. So let me just drag him into the voice chat. Hey Sascha, you're on stream.
Hey Peter.
Okay, so we're gonna go over the rational numbers today. And if you guys are watching this on YouTube, hit a like and subscribe and leave a comment down below. Alright, so let's get started, Sascha.
Alright, so first of all, before I'm able to introduce the rational number, I need to talk a little bit more about the integers.
Okay.
Because right now we just have addition and
subtraction.
That's pretty much it.
Yeah, and the negative numbers, yeah.
So maybe I will give a short survey about how we define the other thing.
Mm-hmm.
And after that we can move on to the rational number. So
Okay.
maybe there will be some gaps in the thing I said, because
Okay.
we probably need another 2 hours if we want to do everything properly, but I think I will leave some gaps that you can easily fill.
Okay.
Okay. So last time. So last time we proved that if x is an integers, then x admits a canonical representation. Last time we showed that x will be equal to either a pair of this form or this form.
Mm-hmm.
And last time where a is some kind of natural number.
Mm-hmm.
And last time we spent a couple of time to show that this decomposition always exists and it's unique.
Mm-hmm.
And we all had one of them, and we said, well, we're kind of sick of writing pairs like that every time. So now we will just write as a shorthand x is equal to a and x is equal to minus a.
Mm-hmm.
So that was what last time we did.
Yeah.
And the benefit of having a unique a canonical representation is now that we don't need to check anymore if our definition is well defined, because now we're able to in each equivalence class to pick a canonical representation,
So
which makes life much easier.
Yeah. So let's say if we wanted to prove something involving the negative integers with the positive integers, right? Do we have to actually make a lambda about what you just wrote, or we don't have to worry about that anymore?
No, so we proved that.
Okay.
So I mean, if I give you just a short summary, so the integers were defined as a pair of natural numbers modulo some equivalence relation. Okay?
Mm-hmm.
And the equivalence relation was basically, well, I can write that down below.
Mm-hmm.
So we said that this pair are equal if they are the same, if those pair represent the same difference, and then in a clever way it means that we have x1 plus y2, which is equal to x2 plus y.
plus y. Yeah.
So previously we had a little bit trouble because we had so element of those were equivalence class.
Yeah.
So they were not just pair, they were a set of pair where all the pair inside of this set are equivalent.
Yeah.
But now that we have canonical representation, now we don't have to worry about choice. We can always pick the canonical representation, and as it's unique, we don't. I mean, there is no other way of defining it because it's unique.
Okay, so it's taken for granted that we don't have to write a lemma for that or something like that.
No, we already went to the proof last time, so.
Okay.
So now we're fine.
Okay.
Okay, so I will do a little survey on the some other properties we might want.
Mm-hmm.
So we call that now we have addition. So last time we defined it,
mm-hmm.
and it was pretty explanatory. We can do component-wise addition.
Yeah.
On those pair, and yeah.
Mm-hmm.
So now we can define, we can basically recover what we had before on the integer. So now we have a successor function it takes an integers and give you the next integer.
Mm-hmm.
So what you will do, you will just take n and give it n plus 1.
Mm-hmm.
And where, I mean, plus, here the symbol plus 1 just means this pair, but from now on I will avoid writing the pair.
So like, quick question, does this have to relate to the axioms that we went over with set theory? I think it's going to be the axiom of infinity, right?
Yeah, so this is like, so the integers as a successor function, this is like one property, one defining property of the natural number, that you can have a section, not a section, but a successor function that take a natural number and give you a natural number. And if you want to describe it very simply, you just add 1 to your number.
Okay.
So now what so this was defined over n, right? Over the natural number. Now we have a completely natural definition over the integers, where we basically just do the same things. It's just that now n can be an integer. It doesn't have to be longer natural numbers.
Okay.
Okay. And okay, so now we want to define multiplication, and usually multiplication is defined using some set of properties. So here it's a little bit interesting because so when we went into Zermelo-Fraenkel set theory, we had an axiomatic theory, right? I list a bunch of axioms that we took for granted, so they are like the atom of our theory.
Yeah.
But you will sometimes hear people talking about the axiomatic theory inside of Zermelo-Fraenkel set theory. For example, here I can state the axiom for multiplication. Oops. And it would be something like that.
Okay.
So I want that x times 0 is 0. And I want x times the successor of a number y is x times y plus x.
Okay.
So basically the second one, if you want, we can just reformulate with the definition above. So we just want to x times y plus 1 to be xy plus...
And sy is basically successor to y, right?
Yeah.
Okay.
So the second point, like the thing I wrote on red and the thing I wrote in blue are exactly the same thing. So we want this nice distributive property of the multiplication over the addition, at least like when you have this very specific cases.
I see.
And it will follow that from this property that you have a distributive multiplication over addition in general. So those are the axioms.
Okay.
But axiom here are not. I mean, we use the same word axiom here in this. We use the same word for axiom of multiplication and axiom of Zermelo-Fraenkel, but those are not the same thing. This I like to think when we have like some object that we'd like to define, and we list like a bunch of properties. I like to call this a wish list.
Okay.
Okay. It's a bit like before Christmas, you do your wish list to Santa. That's kind of the same thing.
So would it be like kind of like saying like, oh, I want to create a game, but I don't know what the exact rules are, but I do have guidelines of what I want those rules to do.
Yeah. So the thing is, you know the rules of the game.
Yeah.
But you don't know if the game is possible to make.
Yeah.
So that's pretty much the problem here. So here we're just basically making a wish list. We're just stating a bunch of properties that we want for multiplication, and we would like a theory of multiplication that has those properties.
Yeah, it's like basically you make the rules, but you don't know if with those rules there's like strategies where it's like, oh no, you're gonna have like an infinite loop, and you're gonna have a game that doesn't end. It's something like that. So you're just like, it's sort of like basically you're just writing it down, but you haven't like produced it as a game yet, basically.
Yeah. Yeah, so for example, if we write like a very bogus axiomatic set, we can have like the properties 1 is contradicting properties 2 and then so on. So for example, you cannot have a theory like that. So it's always a good thing to check that our axiom theory is not empty. So there exists at least one thing called multiplication that verifies those properties.
And before we continue on, I want to say hello to, I think, Zoe Louise 14 just joined the chat. Thank you for joining the chat. Hopefully you're doing well, and hopefully you don't mind learning some math with us. Go on, Sascha.
So I will skip over some details, but so I will assume the following fact: if such a theory of multiplication exists, it has to be unique.
So if such a theory of multiplication exists, it has to be unique. Okay.
So what I mean by there is, so if you think about multiplication, what it does is it takes, so maybe we can define with a little dot, because I usually write multiplication with a little dot. So what it does is it's really a function, right? It takes two integers, so we can think of them like as order pair, right?
Yeah.
And give you back an integers. And what I mean by unique here is, if you're able to find another function like the one the one with this signature, so it takes two integer and give you an integer that check properties 1 and properties 2, then those two functions will be exactly the same.
Okay.
And basically the reason why, so two can help you define, like if you know what is multiplication on, for example, 0, you can define it on 1. Right? Do you see that?
Yeah, so basically, like, I guess the 1, like multiplying by 1 is considered, mathematically, it's considered like an identity?
Yeah, with axiom 2 you can see why, because if we do x times 1, right?
Yeah.
Axiom 2 said, well, okay, first of all, 1 can be written as the successor of 0, right? And axiom 2 tells you that you should have, this should be x times y plus x, right? So we're gonna have x times 0 plus x in our case, right? So I just used the axiom 2. But then axiom 1 tells you that x times 0 is supposed to be 0, so we end up with 0 plus x.
Yeah, which is x.
We end up, and you can pretty much do this game by induction. So you can do for x, so you kind of see what's gonna happen is, if you do it for x times 2, you have x times the successor is 1.
So 1.
Yeah, and now we end up with x times 1 plus x. But x times 1 we just computed before, so it's just x, and the other guy is just x. So we end up that x times 2 is x plus x.
Yeah.
So that's pretty much the reason why such a theory is unique. So the first part kind of tell you what to do with the next, like if you know the value. So okay, maybe I can restate that. So the first part is kind of like initial condition.
Yeah.
Like it tell you what did happen on the base case when you multiply by 0. And basically you can make up all the other value of the multiplication.
Are we assuming that 0 is part of the natural numbers or the integers?
Yeah.
Okay.
Yeah. Okay. And okay, so I said, so you can sort of see why such theories has to be unique, and here you can, if you play a little bit with this definition, you can sort of work out the definition, but I will just state the definition below.
So just to paraphrase what you just said, right? So we have the axioms of multiplication, right? Which basically makes a utilization of the quote-unquote successor rule. So in your example, you basically put like x times 1, which is equal to x times the successor of 0, which technically is basically just x multiplied by 0 plus x, and therefore giving you x as a result, giving you the identity for the multiplication identity.
Yeah.
Like how 0 is the additive identity for addition, right?
Yeah. Yeah. So right now, I just focus on defining addition and multiplication. But at the end, I will just state everything we did with the integers as a neat package that will collapse all the properties like distribution, inverse for addition, identities and stuff like that.
Yeah, I just find it interesting that you just basically replace any number and just basically put an S in front of it, and that's like, oh, that's the number next to it. That's like, you don't even have to write like 2 or like anything. It's just like, oh, just S something, and that's it.
Yeah, I mean, that defines the whole thing, so yeah.
That makes it so much easier. Well, kinda.
Okay, so here I will try not to mess that up. So
yeah,
it's y1, y2, x1, y2. And now we need the other cross term, which is x2, y1. Okay. So, I mean, one can check, but it's a little bit, I mean, I don't really want to do it, but one can check that one can define multiplication like that of the integers. And this definition will check the axiom above. Okay, there's some thing we have to be careful if we want to really check that. So first of all, we have to make sure that this definition does not depend on our pairs.
And x and y are sets, right?
X and y's are elements of the natural numbers.
So they're elements,
X1,
okay.
Yeah, x1, y2, y1, y2s are natural numbers.
Okay.
And here you see I have multiplication involved in the definition, so you might say, well, that's a circular definition. The reason why it's not is because this multiplication, for example, is defined over n. It's not defined over the integer, so we don't have a contradiction here because, I mean, we kind of skip on that at the beginning, but the natural number has a definition of multiplication that you, I mean, you sort of see it in the natural number game that you play on stream a few times. So they have the definition, which is, I mean, pretty much, it's pretty much like the set of axioms give you the value, so don't really have to matter about that. And maybe here, let's see if we can get back some property that we expect.
Okay.
So for example, so last time we defined negative number and positive number, right? So we said that a positive number has a canonical representation as a pair like that, right?
Yeah.
And the negative number has the opposite, right?
Right.
So this is positive, and this is negative. Yeah. And what I want to show, so there is a well-known formulation. So when you go to integer, there's something a little bit fuzzy that goes up with the multiplication, is that you get the sign rules, right?
Yes.
And as you see here, we haven't explicitly asked for the sign rules, but you will see that it will still show up.
Okay.
So maybe we can do I don't know what part of the sign rule you want to check. Maybe we can check a positive times a negative, just to, so maybe we can.
I was about to ask that. Are you actually going to prove to us that like a negative times a negative is a positive?
Yeah, so I will show you. I don't want to do it in general, but I will just show, for example, that 1 times -1 is -1.
Right.
To give you an idea. So this guy, you really have to think about this guy as 1 and this guy as -1.
Yeah.
So if we unravel the definition above, so what we get, so I mean, first of all, we have to multiply the component, but at every time we have one of the components empty is 0, so we get a 0 here, right?
Yeah.
And for the cross terms, so we get, for the first guy, we get x1 times y2, which is in our case 1 times 1. And the other case, we have x2 times y1, but x2 is 0 and y1 is 0, so we get plus 0. So we end up with the pair 0 times 1, which is just a shorthand for
-1.
-1. Yeah.
Interesting. Very interesting.
Also, I can maybe show you a thing. So there's another negative symbol that we can define when we talk about addition.
Mm-hmm.
So this can be thought as a function, but we will use the minus sign to define it.
Mm-hmm.
So what it does is it takes an integers and give you its negation. Okay, so for example, I give you the pair A0. What I do is I just swap the order inside of my pair.
Okay.
Okay. So what the way you have to think about it is I take a positive number and I give you a negative numbers.
Mm-hmm.
And I mean I can do that if I start with a negative number. I mean I just swap the order. And what I expect is that so this thing we can call it as negative inverse, taking the negative inverse, right?
Mm-hmm.
And the reason why it's called like that is because if I have like I don't know, I have let's say I have the pair A0.
Mm-hmm.
And I add the negative pair, like that. Oops, sorry. So I had his pair, but in the negative, like the way I just defined it.
Mm-hmm.
So what it would be by definition, it will be A0 plus. So what is the negative doing? You just swap the orders. So I get 0A.
Yeah.
And then I end up with AA, which is the same as 0, 0. And basically, if I maybe wrote it in the more the usual way we write it, this will correspond to the fact that x plus minus x, where minus x is a number which is just like the negative inverse of x.
Yeah.
You get 0.
So this is basically like the addition rule involving like negative numbers, right?
Yeah. So basically this guy is just a notation for saying that this minus x is an integer that has this defining property that if you add it with x, you just get back the identity on addition, so 0.
So that dash you wrote like such as the integers from to the integers, right? That dash is supposed to signify like the symbol that we need in order to identify the operation, right?
Yeah. So the dash is just like the thing I defined above. Okay?
Like the typical minus sign that we would see in front of a negative number. Okay.
Yeah. But here we kind of get into a little bit of a funny problem. We get into the problem is. So -1 is also an element of the integers, and now we define multiplication, so it makes sense to ask the question: is minus times x equal to minus x? Where the last one is the one I just put in the red box, and the other guy is just multiplication by -1. So we kind of get into that.
Okay.
And one can check indeed that's the case.
Okay.
Okay, so now I'm left, so I define multiplication. Oh, I need one thing I have to worry about. So the integers has an orders relation. So we say let me write the things properly and not be too sloppy. So let x and y be two integers. We say that x is greater or equal to y. And basically it will just be a copy from the last definition we did for the natural number. If there exists some natural number n, such that y can be written as x plus n. And if you want the strictly positive, you just add the extra condition that you want that n is not 0.
Okay, so let x and y be an element of the integers. We say that x is less than or equal to y if there exists an n in n, y is equal to x plus n. Okay. If x is less than y, if there exists n within n is not equal to 0, then y is equal to x plus n. Okay.
So basically, in the first case, we allow equality. So n could be like, for example, 0. In that case, you get x equal to y.
Mm-hmm.
But in the second case, we want to be more restrained about this condition. So we ask that n is not equal to 0 to basically forbid the case x is equal to y, because we want strict inequality.
Okay.
Okay. So I mean, that's basically the same definition we had last time for the natural number, but I just want to restate that like everything works in the case of the integer. There is like no surprise here.
Okay.
Okay. So here I'm gonna write some a little bit of abstraction, because basically we're gonna use it over and over, and if I don't introduce it right now, we're basically gonna prove the same thing over and over. So I will just introduce it once, and then we will use this abstraction to save us some proofs here.
Mm-hmm.
So it's going to be an abstraction. So basically what we have here is that we have a set Z. So we have the integers with two operations, right?
Mm-hmm.
And what we're going to do is we're going to and those operations have some properties, and what we're going to do is we're just going to axiomatize those properties.
Okay.
And the reason why I want to do that, so for now it would not be very obvious why I want to do such a thing. I'm basically just making the thing more abstract.
Mm-hmm.
But the reason is that we're gonna encounter a lot of structure that will have operation like that, where you have like addition and multiplication.
Mm-hmm.
I mean, it's not very hard to imagine. For example, the rational number also have a notion of addition and multiplication. The real number has a notion of addition and multiplication.
Mm-hmm.
Polynomials has a notion of addition, multiplication, and so on.
Yeah.
And even like sequences. So we're basically going to use a little bit of a language from algebra here.
Mm-hmm.
So we say that a set R with two special functions, which we're gonna call plus and times, and those are like are supposed to mimic the.
Is the R supposed to be a regular R, or is it supposed to be the real numbers?
So R is just a set.
Okay. So it's just a regular R then. Okay.
Yeah. And so we have two functions. So we have the addition function that takes two elements inside of R and spits you another element inside of. Just like the way in the integers, if you give me two integers, I can add them together, and what I get as a result is just another integer, right?
Mm-hmm.
So here's the same thing. And for multiplication, you have a similar. Oops, I'm supposed to write this R. So a set with those. So a set with so a set R with those two. Those two functions that satisfy some properties.
Mm-hmm.
And now it's going to be a bit of a pain to the ass to write the whole thing, but let's see if we can remember.
Mm-hmm.
With the following properties. So here I have to be a little bit careful.
Mm-hmm.
So what I want, so there's a few properties I want, so it's going to be a long list, but we have to do it at least once in our life.
Mm-hmm.
So we're going to say there exists an element which we're going to call 0, because you're going to see it's going to pretty much reflect the way that 0 works inside of the integers.
Mm-hmm.
So what it's going to do, it's going to be, so if you give me any x inside of R,
Mm-hmm.
you get that x plus 0 is equal to x.
Okay.
Okay, so 0 will be the, if you want the identity. Yeah, so
the additive, the identity of addition.
Yeah, neutral element for addition. of saying that. Basically, adding pi 0 does nothing. So the second property we want addition to be associative. So what this thing means is if I have x, y, and z inside of R, I don't want to care about the order of the parentheses.
Yeah, this we're all familiar with from like I think like basic algebra.
Yeah. There exists structure where you have to care about order of parentheses, and it's a real pain in the ass to work with those. So what's the third one? So we want every x inside of R to have an inverse, an additional inverse. So for all x inside of R, there exists a y inside of R such that x plus y is equal to the natural element 0.
Okay.
Okay. Okay, maybe let just me check the list so I don't mess it up. So yeah, I want, okay, this one is actually not required, but I mean, in the sense it's not required because I can remove it from the axiom and I can recover it from the other's axiom. But I will just assume it as an axiom because, I mean, not very interesting to prove it. So if you have x plus y is equal to y plus x. So this is commutativity.
And are these are just purely axioms, right?
Yeah.
Okay.
Okay, what else? So you have associativity.
You have associativity, you have commutativity. I think you also have to have distributivity.
Yeah, so okay. So those are basically the axiom for addition. And now I have another set of axiom for multiplication.
Right.
We're gonna assume that a multiplication is associative. So again, the order of the multiplication, the way we put the parentheses doesn't matter. We have x times y. So times z is equal to x times y
times
z. Yeah. And I mean, I already used the fact that addition was associative before because I don't put parentheses everywhere. No.
Yeah.
From now on, we can just write x, y, z. Okay, what else do we need? We need a natural element for the multiplication. So there exists an element which we're gonna call 1 inside of our ring R, inside of our set R, such that for all x inside of R, we have that 1 times x is equal to x. And okay, so those are the properties for multiplication, and now for 7 and 8, we will ask some. So right now we kind of state just like some bunch of properties for addition and multiplication, but we want the two to work nice together. And you already like mentioned it. We're gonna ask from some distributive property.
Yep.
So for all x and y and z side of R, we're gonna ask for the following two distributivity properties. So we're gonna ask that x plus y times z is xy plus yz. Okay. And okay, I'm missing one. Okay, I'm missing this guy. Okay. We also want that x times yz, so we want the other way around. To be xy plus xz.
Wait, is the top one supposed to be like x times z plus y times z?
Oh yeah, I'm sorry. Yeah.
Yeah, I was like wondering like if I was saying your z wrong, that's why I was like a little confused.
So yeah, those are pretty much the axiom we want.
Yeah.
And if we have such a set, we said a set R with those properties is called a ring.
Oh, so this is a ring.
Yeah, and I mean, so as I said, it's an axiomatic theory, so it's kind of a wish list for now. So maybe there exists no theory of exists no set R which has those properties. Maybe that's just like a fantasy we're writing. And one of the exercises we're gonna have this week is gonna show that. It's an exercise I will put on the list for this week. Show that Z with addition and multiplication is a ring.
Is that an exercise?
Yeah.
Okay.
So basically, it basically boils down to check that we have the 7 properties that I stated before.
So show that the integers with addition and the multiplication symbol is a ring, right?
Yeah. Yeah.
Okay.
And also the other part we're gonna show that Z, not Z, but Q. I mean, right now we cannot do it because I haven't defined what it is, but
yeah,
is a ring. And even it's a little bit stronger, it's a field.
and I'm guessing you're gonna find a field in this.
Yeah.
Sure.
So
okay.
yeah. So now that we have rings, so maybe we can just reflect a little bit about the axiom. So maybe we can. I mean, right now I just kind of wrote some logical symbol, and we were very formal about it.
Yeah.
So maybe we can now have like a more casual discussion about the axiom.
Mm-hmm.
So as I said, so the first axiom basically tells you that you have a neutral element for addition.
Mm-hmm.
The other guy is associative, so it just basically means that adding stuff together is not a pain in the ass.
Yeah. It's symmetric on both ways on how you do it.
Yeah. And the third axiom basically tells you that we have inverse element for addition.
Uh-huh.
So 4 is just basically commutativity, so the order of you doing addition does not matter. Which is different from associativity, because associativity is the order of the parentheses, and now it's like the order of the element.
Okay.
And for multiplication, we have like similar properties. It's just that we have some missing, right?
Yeah.
So we get associativity and we get a neutral element. But what we don't have is multiplicative inverse.
Mm-hmm.
So a ring doesn't have multiplicative inverse in general.
Oh, okay.
And for 7, we don't have. We don't have. I mean, 7 is just like kind of a reasonable thing you want to do. So you have like two's operation, and you want them to be somewhat compatible. So you ask for like distributivity law and stuff like that.
Mm-hmm.
Okay, so maybe I can tell you about some missing axiom. I'm gonna put the quotation mark on missing because they're not really missing. They just like we don't really impose them, but we can like add like some adjective to the word rings to make them part of the definition. Okay, so some missing axiom. So maybe I can call it first one. So the first one is if you look back to the beginning, we don't have multiplication is commutative. So if I take two element xy, two element xy inside of R, I don't usually have x times y, which is equal to y times x. So this is called the commutativity of multiplication. And the ring does have these properties that are called ring with that property, I should say, are called commutative. All commutative ring. I mean, usually we will deal with commutative ring in the most of the time. Okay. Except in linear algebra, where we're gonna deal with some specific ring of which is not commutative, which you already know without knowing it.
Commutative ring that.
And then another commutative ring, a ring which is not commutative. You already know one example without knowing it.
Okay. I'll probably be thinking about that while you're lecturing, but go ahead.
Yeah, I mean, I will just take the second axiom, which is something cool, which is so as we said before, so we haven't assumed that multiplication have multiplicative inverse. So if we have for all x inside of R,
Yep.
which x is not equal to 0,
Okay.
we have that there exists some y inside of R such that x times y is equal to 1. We call such a ring. Well, here we don't just have like an adjective like commutative, just commutativity. We straight up say it's a field. So we call such a ring a field. Okay.
So a ring can be a field.
Yeah, but not. Yeah,
but not the other way around, right?
So any field is a ring, but not every ring is a field.
Okay.
Okay. Here I have to confess some unfortunate language difference between French and English. So in English, usually the word field means a commutative ring, which so again maybe I will write it in the bottom. In French, I was supposed to write French with a big F in English. That's also a language difference.
Oh,
in French,
really?
Yeah, the word field is a ring with axiom 2. Okay. In English,
okay.
The word, well, I wrote is ear field, but obviously in French it's not field. In French we say it's a car.
Okay.
Which is, so it's a bit amusing because in English you have like the word fields, which means two different things. So you have like a vector field and you have a field like in algebra like that.
Yeah.
But in French, those are two separate words.
Okay, I figured, yeah.
In French, we call a vector field un champ de vecteurs, which is like in French is like a weed, not a weed, wheat. How do you call the thing to make bread?
Wheat.
Yeah, wheat. I guess you can have a weed field also.
Oh, okay.
I mean, I'm Canadian, so that's possible.
Yeah, it's possible. Yeah, it's possible.
So in English, the word field, and the other way we use the word field. So for in algebra, a field is called a car, as I said before.
Yeah.
And a car in English would pretty much be like, for example, in French we might say un corps céleste, which in English translates to a celestial body. So car is kind of like a body.
Oh, okay.
Like the human body.
Oh, okay.
In English, the word fields is a ring with axiom 1 and 2. So for English speaking country, people said that a field is a commutative ring which also have multiplicative inverse.
Okay.
And if in English you want to say that your ring is not, so you have a field which has multiplicative inverse but it's not commutative, you say it's a divisional ring. In English, we use the word a division ring or ring with axiom 1. With axiom 2 so only. So basically, the translation is not one-to-one if you want, but it's not the same in French and English. So in French, a fill is only axiom 2, so in English that would correspond to a division ring, and a fill in English considered to what we call in French a commutative ring, or in French we say a co-commutative.
Okay.
So that's a little bit of difference. You have to be a little bit careful, and usually when I mean, most of the time we will work with commutative stuff, so we don't have to worry about the difference. But it's kind of just like a funny cultural difference we have to point out.
Okay.
Okay, so maybe I will just be a little bit more hand-wavy. So I will just give you example of rings, so you can have a little bit more intuition about some example of those. So I'm gonna give you some example of rings. So we're gonna go a little bit around what we were supposed to do, but I mean, I think it's going to be beneficial for you at the end.
Okay. So
let's consider the following set.
Yeah.
So what is this guy? So maybe I can write it down. So M2 by 2R is called is the set of all square matrices with real coefficient.
That's what I thought it meant, because I was like, wait, like I saw the subscript and I was like, are you gonna do matrices?
Yeah. So matrix. So you have an obvious way to add like two matrices. So basically you have A0, B0, C0, B0, and then you have another matrix A1 times B1, C1 times D1. Sorry, I didn't meant to put the dot here. I mean, you can just do the obvious thing, just add them component by component, right?
Yeah.
B0 times B1, C0 times
C1.
C1. Yeah, I'm getting messed up with the indices.
Sorry.
D0 times D1, and also you have a notion of matrix multiplication, right? Which I don't really want to write the formula because it's kind of a pain in the butt to write it, but you have a notion of matrix multiplication, and as it's 2 by 2, when you multiply 2 by 2 matrix, you get back another 2 by 2 matrices, right?
Yeah.
So those are have like the two operation we want. So this is a ring.
Oh, okay.
And this one is kind of a very weird one because it's not commutative.
Yeah, because you can't like do a reverse of the multiplication, because there is this, but also usually the product of two matrices does not commute. So maybe I can just Google some very two matrices that does not commute. So you just give you an example. Okay.
I want a 2 by 2 matrix. Or maybe you know some, just I don't remember one top of my head.
That doesn't commute.
Okay, I have an example here I just stole from Stack Overflow, so let's see. Maybe let's look at it. So the matrix 0, 1, 1. So this is our matrix A, and our matrix B is 1, 1, 0. So maybe we can do the matrix multiplication.
Oh, thank you for the raid, Zach. Welcome, raiders. Welcome, welcome, welcome. We're just going over some rules. We're actually going over what a ring is and what a field is.
So here we get 0. Here we get 0 as well. Well, this thing looks like it's gonna be the 0. Well, okay, maybe if I wrote the other way, so this guy is just 0. Unless I'm very bad this today to do matrix multiplication.
Yeah, happy Tuesday, Zach.
Which is not uncommon.
Yeah.
So here what we have, so I have 1, 1, so this guy is 0. And this guy is not 0, it's 1 times 1, it's 2.
Mm-hmm.
This guy is 0. This guy is 0.
Mhm.
Okay. So here you see the way we did the multiplication, the order we did the multiplication matter, right?
Yeah.
This is A times B and this is B times A. And as you can see, those are not equal.
Mm-hmm. Hence not
So this is a-
commutative.
Yeah. So this ring is not commutative. And I mean, this ring is pretty bad if you look at it as a ring because it has very bad properties. It's not a very nice one. So as you said before, there exists like matrices that does not have inverse, right?
Yeah, it doesn't look symmetric. Like, I guess, like, in the way it's like you can solve them in this particular fashion, yeah.
Yeah. So maybe I will just use a little bit of your knowledge of linear algebra. So I mean, I don't know if you know this property, but a matrix A is invertible
Uh-huh.
if its determinant is not 0.
Dang, I gotta review that. I know I know what you're saying, but then I'm like, oh wait, invertible. No, I don't think I remember that very well.
Okay. So we can maybe assume that. So if we found a matrix which is has a 0 determinant, then we all automatically know that it's not invertible.
Okay.
And for example, this matrix has no invertible elements.
Okay.
It cannot you cannot inverse this matrix. There is no multiplicative inverse to that.
Okay.
And it's even weirder. So usually in the integers, if you take so maybe we can call this axiom 3 maybe, which is an additional thing you can have.
Okay.
If for all x and y inside of R,
Mm-hmm.
you have that x times y is equal to 0. Okay. So if you take two elements inside of your ring, and you found out that the multiplication give you 0, you must have either x is equal to 0 and y is equal to 0.
Mm-hmm.
Or, sorry. You're supposed to be or. And rings that satisfy this property are called integral. A ring that satisfies three is called an integral ring. In English, you also use the word domain.
Okay.
But yeah, I usually like to call them integral because I'm French.
Oh, so
Okay.
basically like the domain that we're so used to in graphs, right? So like, x is like the domain within like say a graph within an xy graph. Right?
Well, not really. I'm not exactly sure why in English you use the word domain.
Uh-huh. Oh, okay.
It's not really related to a graph, but what this property says is if you take two elements and you find the product is 0, then either one of those has to be 0.
Be 0.
And the integer z
Mm-hmm.
is integral. Is an integral ring, so it has these properties. So if you have x and y is equal to 0, you must have that x is equal to 0. Actually, you know this property has another way, because there is a very well-known consequence of that that I can state, that you use all the time when you do basic algebra.
Are you talking about linear independence?
No. So you say sometimes when you solve equation,
Mm-hmm.
you have like something like that, right?
Yeah.
Okay, and assume that a is not 0.
Mm-hmm.
Then usually when you have that, if for example you want to isolate x, you just want to know what x is. Usually you will see something like that, right? You will say, well, I can just cross out the a's, right?
Yeah.
Well, this properties is not always true for a ring. You must have that it's integral to be able to do that.
Like
So maybe I can show you. So usually in a ring you cannot just cross out the terms. So I will give you a counterexample to these properties. Okay.
Okay.
So maybe I can show you this is false in general. So let's go back to matrices because those are very bad. It's a very bad ring. So let's take A to be the matrix 1, 0, 0.
Okay.
Take B to okay, maybe I will use the same symbol I use here. So maybe let's call it X. Let X be the matrix 0, 1, 0.
Okay.
And takes y to be basically the same matrix, just you're gonna scale it a little bit. So let's maybe put a 2 here, so that
Okay.
x and y are different.
Okay.
And now let's have a look to a times x.
Okay.
So what is this, guys?
Let's see. So multiply that 0 and then 0. Like it's practically like I think it's like 0 all around.
Yeah, exactly. And I mean, for a times y, there is no. I mean, that's basically this here the same thing. We just like scaled it a little bit by 2, so we get the same thing.
Mm-hmm.
So we also get the multiplicative. We also get the 0 matrix.
Okay.
But what is funny here is that neither of those matrices are 0, right? Nor
Right.
a, nor x, nor y are 0.
Right.
And if so what I get here is that I get that a times x is equal to ay, right?
Mm-hmm.
But this does not imply that x is equal to y.
Y. Yeah.
Because clearly here they're different.
Uh-huh.
So when we're not over an integral rings, we have to be really careful about canceling out the terms like we usually do, because sometimes it can be false. For this example, you see that this clearly doesn't work.
So, like, if you were working, say, in abstract algebra, for example, right? Like, if we were given that same expression, you don't know what x, y, or a is. They could be anything from, like, a number to, like, say, a matrices or something, another mathematical object, right?
Yeah.
Okay. So how does what you wrote about the determinant here, the invertible part, how does that relate to what we're discussing right now? I'm trying to find the connection here.
Oh, so okay, so this one was to show you that so okay, this part maybe I can go back. So a non-zero matrix may not have a multiplicative inverse.
Okay. All right. Yeah.
So basically, matrices. I mean, here I took 2 by 2 matrices, but you can do exactly the same exercise we did with n by n matrices. Except when n is equal to 1. In that case, we get something a little bit different. But for n bigger than 2, or equal to 2, we get a very bad ring. It's neither commutative, it's neither a field, it's neither an integral domain. So it's a pretty messed up example.
Okay.
But it's a pretty important one, nonetheless.
Okay.
So maybe here I can prove it. I mean, that would be a part of the exercise this week. Is that Z is a commutative ring? Is an integral commutative ring. So it means that. In other words, we have. So what was the? I forgot my naming scheme I gave to those properties. So 1 was commutative and 2 was a field. Okay, so it satisfies 2 additional axioms. It satisfies 1 and 3.
Just 1 and 3, or is it 1 through 3?
No, 1 and 3. It does not satisfy 2.
2.
So maybe I can write it. It doesn't satisfy 2s. So in general, you cannot have multiplicative inverse.
Okay.
And if you're kind of coming from the same point from the viewpoint that you want to be able to solve equations, Z is kind of incomplete in that regard.
Okay.
Because, for example, I can write the equation 4x, which is equal to 1. If all the coefficients are inside of Z, right?
Yeah.
But yet the solution will be something which is not inside of Z, right?
Yeah.
Therefore, we're kind of missing we're missing some numbers, right? So So we kind of have to fix z, and for that we're gonna introduce a new set, which is as you may have guessed, is the rational number.
Okay. And that's basically the lead up you wanted to show us, right? To basically show the problems and then what leads us to actually like think about how to create these numbers, right?
Yeah. And okay, so Z was kind of, I mean, okay, probably if we go back to what we did like a few streams ago, so we started with basically Zermelo-Frankel set theory, and I mean, we kind of get some nonsense that like somehow the 0 was the empty set, and like 1 was like the set that contained the empty set, and like some very weird, strange way, right?
Yeah, by using cardinality of a set.
Yeah, like we would never use that to like to tell like a children what is a natural number, right?
Yeah, because sets like it makes it too abstract.
Yeah, and for the integers, I mean, it was a little bit better, but at the same time, it was kind of weird to think of like integers as pair of numbers, right?
Yeah.
Even though we kind of fixed that with the thing we did last time. And what you're gonna see is that I think like among the three like basic number we can define, the rational is probably like the most intuitive one to define. Okay, so definition of Q. So what is element of Q? I mean, just let's start with an informal like a survey of what is the so what is the rational. So element of rational should be like some kind of fraction, right?
Yeah.
I mean, those guys are basically like pairs, right?
Yeah.
We should have to be a little bit careful. And if we go back to like elementary school, like maybe I have two fractions. I mean, obviously I will not write like something in elementary school. You say that those two are equal if you have what?
Those two are equal if basically if A1 is equal to A2 and B1 is equal to B2.
Not quite, right? Because for example, the fraction 1/2 and 2/4 are equals, right? But the numerator and the denominator, I mean, none of those are equal. So we have to be a little bit more careful here.
Right.
So do you? I mean, can you think about when two fractions are equals?
Well, the first part I said, that's like probably one condition, and then like the second thing would probably they can also be equal if A1 and A1 over B1 shares a multiple of let's say a natural number that can be reduced to back to A1 and B1.
Okay, maybe I will write something. Maybe that's what you meant. So, I mean, usually when I was in elementary school, the teacher was telling us that two fractions are equal if we have like the cross test, right?
Yeah, cross multiplication, yes.
Yeah. So if we have 1 times 4 is equal to this product, right?
Yeah.
And I mean, this thing from elementary school. So maybe if we write it explicitly on the general fraction like that, you will get y1 times b2 is equal to a2 times b2. Okay. And you might think that like the rational number is going to be a complicated mess, but that's actually the thing. I mean, that's pretty much the thing we're going to use to define them.
Okay.
So let's start with the proper definition. So proper definition. So the set Q, I mean, just as a set, is going to be the integers times. Maybe I can put a little. Oops, sorry. It will be defined as that, okay? So it will be pairs of integers where the second integer is non-zero. Okay.
So, what does this dash mean? Like
so okay, maybe I can write it above. So it just means that this is the set of integers such that x is not equal to 0.
Oh, okay.
So we're just removing 0 from our set.
Okay.
And so those guys will correspond to pair, which is our basically fraction. But as we said before, I mean, we can have like two fraction which does not look like the same. Like for example, 1/2 and 2/4, but they're still the same as fraction, right? So we need to add some equivalence relation. And basically, we're just gonna copy the definition we wrote before. So we say that the pair A1's B1 is equivalent to A2 times B2.
B2, yeah.
If we have A1 B2 is equal to A2 B2. Sorry, here I did a mistake. I'm sorry. This is supposed to be a 1.
B1, yeah.
Yeah. So the how do you call it in English? Cross multiplication.
Yeah.
So we're gonna say the cross multiplication test. And I mean, I will not spend too much time on that, but we can show that this guy is an equivalence relationship. Okay. So now we're happy. We define a set, which looks like the rational that we know. Also, okay, just for notation, instead of writing the pair A1 B1, we're gonna instead write the fraction.
Okay.
Okay, so it's just a notation thing, but. I mean, it's more natural to write it like that. I mean, it's more fast. And okay, so now we kind of back in the same problem we had with integers, right?
Right.
I mean, we just gave a set right now, and we kind of have to show it's a reasonable thing, right? So so maybe we can make sense of some of the statement. For example, as previously we did. We'd like to make sense of what it means for. So we know that the integers are inside of the rational, right?
Yeah.
We have to make sense of that.
Okay.
Like the same way we make sense of what it means for the natural number to be inside of z, right? We have to do like the same thing again. Okay. So I don't know. Do you remember the way we did it? In here, I should put quotation mark because it's not really. I mean, it's not literally true right now. We have to do an extra identification to be able to do that. But
yeah, like so basically, you were trying to incorporate the integers into the rationals, right?
Yeah.
So. In order to do that, don't we have to like not an axiom? What am I thinking about?
So last time we did like something very similar for the natural number inside of the integers, right? So do you remember the way I did it?
No, I don't really remember.
Okay, so what I did is I did an embedding, which is a map. So last time, I mean, maybe not last time, but maybe 2 times ago, I built some map. I don't know all the way I call it. Maybe I call it phi. I don't remember.
Yeah.
Which take a natural number and give you an integers, right? And what it did is it took an n and put it inside of n0, right? That was our map. And we had like to make sure that this one was 1-to-1, so it does not like squish some natural number accidentally. So we have to check that this map is injective. And last time we did it together, and I mean, it was not really hard, but we did it. And now we have to do a similar thing. So maybe I can call this map psi. I don't know. We have to define a map from Z to Q. which is gonna be injective and basically be a copy of the integer inside of Q. Okay.
Okay.
So here you really have to think. I mean, usually if we were like just like casually talking, like I will say, what does it mean for the integer to be inside of Q? Like, can you show me like what an integer looks like inside of Q?
Like what does a rational number look like compared to like say from like Z to Q? Is that what you're asking?
So okay, for example, you know, like you can say that 4 is a rational number, right?
Yes.
So how could you show me that?
Basically, you can write it as like, I don't know if ratio is the right word, like between two, like integers, or
Yeah,
like,
can you-
or natural numbers.
Yeah, so you can write it as a fraction. Yeah, this
Yeah.
I agree.
Yeah.
So can you give me, like, for example, how would you like write 4 as a ratio of two integers?
Such as like 8/2, like 16/4.
Yeah, is there like a more easy way of writing it? Like the most basic way you can think of it, because 16/4 is kind of complicated, right? Is there like an even simpler way of writing it?
4/1.
4/1. So, do you agree that it makes sense to take an integers and put it on the fraction n/1?
Yes.
That sounds like, I mean, that's usually the way, like, I mean, that's usually what it means for an integer to be a rational number, right?
Right.
You can, I mean, usually that's what they taught you in school. They say like, so what it means. I mean, what is so they tell you, well, an integer can be seen as a fraction. You just have to remember to put the little 1 in the denominator at the bottom. So we're gonna use this. I mean, high school definition, if you want, of why an integer is a fraction. But as I said before, we have to make sure that this map doesn't squish some integers, so we will check that this map is injective. So I claim that psi is injective. Okay.
Okay.
And now it's going to be a good revision for you, because you have the exercise from last week where you have to check that maps are injective, right? I mean, you have like some... you have to play a little bit around with those definitions. So I will show you. So I will write it properly so you can have all the details and you can use it as a template if you want. So let NAM be. Okay. First of all, what it means. So first of all, we have to make sense of all the words, right? So maybe. I mean, here the map phi is defined above, so we don't really have to worry about it.
Yeah.
But the word which is probably the most problematic one is the injective word.
Injective
Right?
one. Yeah.
So maybe we can just recall. So recall phi is injective. Oh boy, what on earth happened with my pen? Is injective if for all x and y inside of z, if we have that phi of x is equal, I don't know, he doesn't like doing a parentheses, he wants to do square lines like that. Okay. If we have that f of x is equal, not f of x, but psi of x equal to psi of y, so they both equal, we want to conclude that x is equal to y. So this is a definition of injective. So here maybe I will just guide through to the proof. So first of all, we have a quantifier for all, right? So we have to take x and y to be arbitrary. So let x and y be some integers. Okay. And now we want to show this implication. So maybe I will just put it inside of a green square like that. Okay, and okay, so you did a little bit of truth table, right?
Yeah.
Okay, so maybe I have a proposition P here, and I have a proposition Q here, and I have P implies Q. Yeah, I just want to just want to realize what the truth table are saying and how it's relevant to a proof. So I will just show you.
Okay.
So we can do all the cases. So we have 1, 1, 1, 0.
I guess this could be a small exercise for us to think about.
Yeah. So what I'm missing, 1, 0. All right. So I mean, here I just wrote all the possible case you can have. So when I have a 1, it means true, and when I have a 0, it means
it's false. Yeah, that's what I was thinking.
Yeah.
So basically, if you have P implies Q, if P is true and it implies Q, then that means it's 1 or true.
Yeah. So if P is true, Q has to be true, right?
Yeah.
So this implication will be, I mean, in that case, P implies Q would be true. If we have 1 is true, but the conclusion, so sometimes P is called
false.
Sometimes we call this the hypothesis.
Yeah.
And this guy is called the conclusion.
Yeah.
So if the hypotheses are true but the conclusion is false, then we get a problem. We get that's false.
Yeah, it's false.
Right?
Yeah.
And what about the two other cases at the bottom?
So if P is false but Q is true, then that would probably indicate that I'm thinking it's true because the end result is true.
Yeah. So the hypothesis, is like some kind of condition, right?
Yeah.
If you have those conditions, no matter what, you will have like this conclusion, right?
Yeah, because I immediately thought of proof by contradiction or contrapositive in that example.
Yeah. And what about if both are false?
If both are false, then like I'm probably tricking myself, but at the same time, like I would think it's false because they're both false.
No, it would be true.
True. That's what I thought. I thought it was gonna end up like being just true. Yeah.
Like think about it like insurance. So you have like insurance policies, like we're gonna cover you in those cases, right?
Yeah.
Oh, maybe it's not a good example. Never mind. Forget about it.
No, I think like an example of it would be like it's like basically someone tells you something that's not true, but then it was like I guess like when they witness like something that is true, but then they put something that's not true in context. Like say if someone witnesses 2 events, but then they give totally different interpretations of those events, then basically something false ends up becoming true because something happened, I guess. That's like the best way I can summarize it.
Okay. Maybe I found an example which is very concrete and very simple, but yours might be good as well.
I was thinking of conspiracy theories mainly.
I was thinking about warranty for a computer component. So basically, you can think of a warranty as some kind of implication, right?
Mm-hmm.
And on the left, the hypothesis, like the warranty policies, like you shouldn't like do stuff, like you shouldn't like put your GPU inside of your bath or something.
Yeah.
So imagine the water, like there's like some policies. Yeah. And for example, in the first case, it says, and the conclusion is we will like honorate our warranty. So, for example, if the GPU breaks, then we will replace it.
Yeah.
So let's say your GPU break, and now we go through the problem. So the P is the have you followed the policies? So if you follow the policies, then we're gonna. I mean, obviously, if you did like everything we told you, like to how to use our product, and your product break, then obviously we're gonna underrate our policies and give you a replacement, right?
Right.
If you did everything, I mean the second row would be saying that you follow our policies, but we did not underrate our agreement. In that case, we would have violated the warranty policies, right?
Right.
So this cannot happen. I mean, otherwise you can probably sue us, or
Yeah.
it's not fine. And the other two cases are like, well, you violated our warranty policies, but I mean, in this third case, well, even though you violated our policies, we still like give you a chance. We still like give you a replacement because we're a nice guy. I don't know.
Mm-hmm.
But we didn't have to, right?
Mm-hmm.
There was, I mean, basically the contract is irrelevant here, right? It's just the fact that we're nice guys and we said, well, shit happens, so we're gonna give you a replacement. And Zero is like, well, we just follow our policies, like.
I mean, when I look at this, let's see, both are true.
Maybe this is not a good example, but basically what I want you to realize is if the hypothesis is false, the conclusion can be whatever.
Yeah. That makes sense. But like, if you guys want to look up more on this point, I would suggest do like logic and truth tables. That's because I get what Sascha is saying, like, because like the way I look at it, this is the same interpretation as it seems like P or Q. It almost looks kind of similar to me.
Yeah, it's possible to write implication as a combination of or and not.
Yeah.
But I mean, it's not very practical. But here, what I want to stress you when you do a proof and you have an implication like that.
Yeah.
Is that okay? Maybe I can just put some colors here. So maybe you can have a guided color. So in the statement I'm trying to prove, I have a quantifier for all, right?
Yeah.
And this is represented in my proof as using the word let x and y be integers, right?
Right.
And as we said in to show an implication, you have to show that if the hypothesis holds, you must have the conclusion, because otherwise the implication will always be true. So we have to assume that psi of x is equal to psi of y. So maybe if I use color, what I did, I just assume the left part of the implication.
Okay.
I mean, if you were a logician, you would probably even add a statement before the thing I wrote. I say, well, if the hypothesis is false, then obviously the conclusion can be whatever, so the implication will be true. Will be true. But I mean, usually we're a little bit lazy, so we just if the hypothesis doesn't hold, then we just don't bother. So basically, the only thing we have to check is the Okay, so I mean, the two boxes I just wrote here, those were like completely like logical statement. Like they're just like addressing some logical like formalisms with the proof. Now here, so this is just logic, right? Just what I wrote there. Now we're gonna do mathematics. So we're gonna do some mathematics to conclude that x is equal to y. Okay.
Okay.
So maybe a good thing we could do is probably just restate what's the definition of psi, right?
All right.
So that we said that psi is very simple. We just take some x and we put it on this, right? And the same as goes for y, right? So now our hypothesis that say that psi x is equal to psi y. So psi x is equal to psi y is equivalent to x over 1 is equal to y over 1, right? And And now, okay, so now here we have like a statement which says that x over 1 is equal to y over 1. So maybe we can put a layer, just a little bit of parentheses. So this is inside of Q, right?
Mm-hmm.
But we had like some equivalence relationship inside of Q. We defined what it meant for two fractions to be equal, right?
Mm-hmm.
It means that we have the cross ratio, right?
Yeah.
Does, so maybe we can write something like that. Does by definition, maybe we can just write by definition of equality, side of Q. So it means that so basically we have by the definition of equality we have that x times 1 is equal to y.
What does it say after equality?
Inside of Q.
Oh, okay.
So I mean basically what we wrote before, like what it means to two fractions to be equivalent or equal inside of Q.
Okay.
It means that we have the cross ratio like that. And now we know from like what we did before.
Mm-hmm.
So we know that, for example, multiplying by 1 an integer will do nothing.
Mm-hmm.
So using that 1 is the neutral element, for multiplication, we have that x is equal to y. Maybe I can. Okay, here I'm missing colors, but
Mm-hmm.
if I go back to in our logical statement,
Yep.
I just got the conclusion, right? I just got x is equal to y.
Mm-hmm.
And now I can maybe just add a little statement. So as x and y were chosen arbitrary, I might butcher this word, were chosen arbitrary, we have that for all x and y side of z, psi x is equal to psi y, imply that x is equal to y. So we showed the logical statement, which is equivalent to say that psi is injective. And now we're done with the proof.
So psi x equals psi y equals 1, right? Is that what you're
Implies, sorry.
Oh, implies, okay.
So basically we basically just state that we proved the thing with in green above.
Which is equivalent to say that psi is injective, right? That's what you wrote? Okay.
Yeah. So hopefully I was able to give you like some indication for proof writing in that thing.
Yeah, that actually helps.
Yeah. So basically like everything where there's like boxes, this is like more like logic.
Mm-hmm.
And this little paragraph here is like all the mathematical content of the proof.
Okay.
which was basically, I mean, if we summarize our proof, it was basically just like rewriting what it means for two fraction to be equals. That's pretty much our proof.
Okay, so thus we have the integers
inside of Q, right?
Inside of Q, but we haven't. So with this, do we have to actually prove that there are also numbers in Q that are not in Z, and thus like basically giving us the structure for the rational numbers, or we don't have to do that?
We don't have to do that. I mean, it's a good thing like for us, like to show that there exists like element which is inside of Q, which is not inside of Z. But we don't have to do it.
Okay.
I mean, we can do it. Like for example, we can like pick like a specific example, like 1/2, and show that 1/2 cannot be an integers. But it will follow from the fact that we're gonna prove later on. Okay.
Okay. No, because like my question is that does this proof actually prove that there are certain rational numbers that are not in the integers, or it only proves like one part of it, which is basically saying that the integers are in the rational numbers?
Yeah, it proved that. Yeah, it proved that. Yeah, so we have that.
Okay.
We don't have the other way we don't have, but it will follow from the ring structure, because what we're gonna show is that Q has multiplicative inverse. It's a field. And Z doesn't. I mean, okay, I guess we have to show that Z does not have like some element which does not have multiplicative inverse.
Okay.
Like for example, 2 cannot be inverted inside of Z because multiplicative inverse would be a half, which is not Q. Right?
Yeah.
But once we do that, we automatically conclude that, for example, if we show that, for example, in Z that 2 does not have a multiplicative inverse, and if we later on prove that inside of Q every non-zero element has a multiplicative inverse, but then it followed that the multiplicative inverse of 2 has to be something which is not an integers.
Yeah, because like I think like the thing that I'm wondering about is that, do you actually like, because we already have an idea of what Q is going to be, right? It's going to be like a fraction of some sort. But my question is that if you already know the structure of what Q's is, you just have to prove that basically it's in, like basically a subset of it is the other numbers before it, such as like the integers and the natural numbers. So with that, I guess that argument in mind, is it necessary to actually prove that there are elements of Q that are not in any of the subsets that come before it? No, right?
Well, no. So yeah, exactly. So if our logical statement is just that Z is inside of Q, I mean, what we want to make sense of, we don't have to show that the opposite. We don't have to show that there is an element of Q which is inside of Z.
Yeah, because I was thinking about it logically, like from like sets, what we know about sets, and like there are some stuff in sets that you don't know if it's like infinite, for example. But you don't need to know that all the infinite terms just to prove something involving that set.
Yeah. Actually, we're gonna show it a little bit later, but I don't want to do it right now because I kind of want to go to stock analysis, so I'm kind of speed running.
No, it's fine. It's fine. It's okay.
But later on, we're gonna show. I mean, we could do it right now, but I just don't want to spend the time it. But we can show there is actually a bijection between N and Q.
Okay.
So they basically have the same amount of elements.
Oh, okay.
Which is a bit weird. Okay.
Yep.
So now what I want to do is, so I want to be able to, so one of the exercises I want to give you for this quiz is to show that Q is a field.
Okay.
So now what I have to do is I have to define the arithmetic operation on Q.
Okay.
And basically we're just gonna steal the definition from high school.
Okay.
So let's start with the easy one. So defining multiplication. So again, so we want to have a ring. So a multiplication will take an element inside of Q. But two elements inside of Q. So you can sort of think as a pair, and it will give you some another rational numbers.
Right.
And the way we're gonna define it is like, let's say a1 times b1, a2 times b2. So here I will let you think about what you know about fraction.
Mm-hmm.
So what would be like a good definition for multiplication?
Multiplication by fractions, right?
Yeah.
I mean, when I think back on it, like, basically, it's like a...
Yeah, that would be the definition.
Yeah, that's mostly how I think of it, yeah.
Okay, but now we have kind of an issue, right?
Yeah.
Because, as we said before, so, I mean, this guy is really a shorthand for the pair a1, b1, right?
Uh-huh.
I mean, if we want to be very precise, we would like put some square bracket to say it's a side of an equivalence class, right?
Yeah.
So we kind of have the problem that, I mean, it's basically the same problem we had with the integers. We have to check that our definition is well defined. It does not depend on the choice of a1 and b1.
Right. Because like if we just went with what I wrote, right, it seems like I just made that up out of thin air. We don't have like proper structure in it.
Yeah, I mean, it's not even clear it's well defined, right?
Yeah.
Because maybe I can, like, I don't know, maybe a1 times b1
can be like yeah, it could be like
a half.
Yeah, it could be something like that.
Wait,
yeah.
we can be 2/4, right? And maybe this definition is is not well defined. We get something different.
Right.
So we're gonna check that this is well defined. I mean, pretty much the same way we did it last time.
Mm-hmm.
I mean, last time I think I did it for addition.
Uh-huh.
Okay, so how does it work? So let's. The links.
Okay. Just a little technical difficulty, guys.
Yeah, bear with us.
Yeah, bear with us, please. Click that.
All right. So what I was saying, so I want to check that our definition is well defined. So let me. Oh God, why is it so thick?
I think that's how they usually start it as default.
Yeah, I don't get it why, but. So we said that a1 times. So we define multiplication as that, as Peter suggested, which is like I mean the high school definition, if you want.
Yeah.
But we have to check it's well defined. So what it means. So what is boiled down to check it's well defined? It boils down to check that if a1 times b1 is equivalent to like some other fraction like x1 times y1, let's say, and we have the same thing for a2 times b2, which is equivalent to x2 y2, we want we want the thing we wrote on the top here to be compatible with the fact that those two fractions are equivalent. So we want the product of those guys to be equivalent to the product of those guys. Okay.
Okay.
Hopefully now you can see, right?
Yeah.
Okay, so we're gonna prove that. Proof. I mean, basically it's gonna be a mess like the last time we did it, where we had like a lot of things gonna happen. So, okay, first of all, I mean, in this kind of problem, we sort of have to like write everything explicitly. So let's maybe rewrote those multiplication here. So we said that a1 times b1 times a2. Sorry, I'm supposed to put the dot here. As you said, is a1 times a2 b1 times b2. And for the other guys, we have x1 times x2, y1, y2, which is x1, x2, y1, y2, right?
Mm-hmm.
And we would like to show that those two are equivalents. Are equivalent.
Mm-hmm.
Sorry, this is supposed to be a y, really not the pretty one. All right. So we basically have to check when we do the cross ratio with the cross multiplication test with those two fractions, we get the same thing.
Mm-hmm.
So we want to show that it's going to be a mess. So it's going to be a1 a2 times y1 i2 is equal to x1 x2 b1 b2. Okay, this is just the equal. This is just checking that this fraction and this fraction are equal. It's just now that our fraction is so big that it looks like a mess. So
Yeah.
that's our goal. And now we're gonna use our hypothesis that a1 is equivalent to y1 and so on. So using the fact that maybe I will just write ai bi, something like that, which is equivalent to xi. So I don't have to unravel the definition 2 times.
Mm-hmm.
So the fact that those two are equivalents means that we have the cross multiplication works. So we have ai yi is equal to bi
And xi.
Yeah. For I, which is either 1 or 2, right?
Mm-hmm.
And now what we're gonna do is we're gonna basically do the same thing we did before. We're just gonna we have here is kind of like general relativity, right?
Yeah.
You have one equality, but in fact it's 2, right? Because
Mm-hmm.
we have the case y equal 1 and we have I equal 1 and I equal 2. So what we're gonna do is we're just gonna write them out. So y1, a1, i1, b1, x1. This is one of the equality, and we have a2, y2, b2, x2, right?
Mm-hmm.
And now what we're gonna do is we're gonna multiply the left side of both equation with the right side of the other equation.
Mm-hmm.
So when we do this multiplication, we end up with so if we write it very formally, we get a1, y1, a2, y2, and the other side we get b1, x1, and b2, x2. Okay.
Mm-hmm.
Now we have kind of a mess of an equation, so now it's a good idea to look at what our goal is. So our goal is to show that it's basically show this. We have this equality, right?
Right.
And here it's pretty much the same thing we did last time. So we can use associativity and commutative of multiplication to reshuffle the way we wrote that, right?
Yeah.
So we just have to change the order and change the parentheses, so we get that. y1, y2, b1, b2, x1, x2. Okay.
Mm-hmm.
And maybe we can put a little star here and say something like, but star is exactly the identity we wanted to show. The equality we wanted. Equality we wanted. Thus, multiplication is well defined. Okay.
Mm-hmm.
So we were quite good. We were able to define multiplication.
Mm-hmm.
And usually like checking the two. Usually when you work with quotient set like we do, like when we have an equivalence relation like that, you always have to do this like painful task of checking that the operation you define on your quotient set is actually well defined. And usually it always like end up doing like some unravel of the definition like that.
Okay.
I don't really. I cannot really think about one case where checking that something is well defined on the quotient is very complicated. Usually, it always ends up doing like that.
Mm-hmm.
Usually it's harder to find something which is well defined.
Mm-hmm.
Okay, so now we're gonna do addition.
Okay.
So again, we're gonna. This time I will not do it all the way through because I don't want. Basically, I will have to check again. It's well defined, but we'll probably leave you as an exercise so you can practice that.
Okay.
But here's the important thing. How would you define addition of two fractions?
Like when we think back, because the one condition is that you want the denominators to be equal.
Yeah, you want. Usually yeah.
It would be written like, oh, that's too thick.
That's a thick boy.
Yeah. So usually it would be like. No, actually.
Yes. Yeah. So this will be yeah. So the point is that you need to have the same denominator, right?
Yeah.
And what you do is you basically force it to have the same denominator by multiplying by whatever you have on the other denominator, right?
Yeah.
So I will leave as an exercise.
Mm-hmm.
Check this is well defined. In the same fashion we just did with the other with the multiplication. Okay.
Okay.
Okay. What I want to say next.
Mm-hmm.
Okay. And that will be part of the exercise. Basically that's the exercise I gave later. I gave previously. But the thing now I want you to check is that you with those operations is a field. Okay.
Okay, so another one is so multiplication and addition in Q is a field, right?
Yeah. So,
Okay.
so basically, you have first to check it's a ring, and then after that, you have to show that it's commutative, but this will not be very hard to check.
Uh-huh.
And then you have to check that every element inside of Q has an inverse.
Okay.
Given that your element you started was not 0, otherwise.
Like, so proving that it's a ring, right?
Yeah.
Is there a certain technique to prove that it's a commutative ring, or there's no difference in like actually proving something is a ring?
But checking the commutative part, you just have to show that AB times XY is equal to XY times AB.
Oh, okay.
So it's a separate case. Usually you first show it's a ring, like with the axiom I gave you, and then you show it satisfies the commutative property and also it's a field.
Oh, okay. So with all this in general for today's lecture, do we actually have all of the rational numbers, or do we only have a certain section of them? We
have all of them.
Okay.
And right now I just want to do add a little bit of exercise. I just want to add a little bit something. So
yeah.
So it's kind of funny because at the beginning everything was a set, right?
Yeah.
But now we can encounter some other kind of mathematical structure, namely a ring, which has more structure to it.
Yeah.
It's not just like a set of elements, it also has like other operation like addition and multiplication.
Yeah.
And this will essentially, I mean, that's a very common pattern you will see over and over in mathematics. We will have to redefine some stuff that we already defined, but we wanted to preserve the structure we had here.
Okay.
So maybe I can just introduce a definition. I mean, that's something which is gonna maybe help you.
Okay.
I mean, you have to show first it's a field, but okay. So definition. Let R1, and here I'm gonna use like some lower script notation just to make sure that we're talking about the same thing. So let's R1 with those things, with addition and multiplication defined like that, and R2 plus 2 multiplication by 2 be rings. Okay. A function so a function, let's maybe call it f, from R1 to R2 is called, and now there's gonna be a word that you're gonna heard over and over and over in the mathematics. Sometimes you don't use this specific word, but usually it will be morphisms. In our case, it will be a ring morphisms. And what basically will do, so previously when we talk about function were only like defined as mapping something from a set to a set.
Okay.
But here we have more, right?
Yeah.
We have a little bit more because we have structure, right? We have addition and multiplication. So what we're gonna do, what we're gonna ask is that f play nicely with those.
Okay.
So we're gonna ask the following. So we're gonna ask that f of 0 maps. I'm gonna put a little 1 here. So it maps the 0 element of the first ring to the 0 element of the second ring. Okay.
All right.
Oops, sorry, it's supposed to be a 2 here. And I'm gonna ask the same thing for the multiplicative elements.
Okay.
For the natural element. And after that, I'm gonna ask that it play nice with addition. So x plus y will be f of x plus f of y. Maybe I should add for all x and y side of part 1. And I will ask the same thing for multiplication.
So why does the multiplication symbol and the addition symbol all have like subscripts of 1 and 2 in it?
Because 1 is defined on so f is a map from R1 to R2, right? So x and y, for example, are an element of R, right?
Yeah.
So when I do this addition, I mean I'm doing it inside of R1, right?
Oh, okay.
And here, here I took the image, so f of x is now part of R2, right? So now it does not make any sense to be with a 1, right? Because now it's living inside of R2, right?
Oh, okay. It's just basically showing that these two operations within different mappings are equivalent, right?
Yeah, so basically it preserve addition and preserve multiplication.
Okay.
So that's the way you have to think about it. So a function is kind of so a function in general is kind of a stupid thing because it does not remember any structure. You just like map some stuff. I mean, like can be like a very chaotic map, you know?
Yeah, because I think we're so used to thinking of functions as actual equations, when in actuality they're just putting something from one set into another set, basically.
Yeah, exactly. And like as I said, like I showed you before, we had like the Pokemon example with the colors. You know, it's just like you can map basically anything to anything. There's like no rules. Like,
So from your definition right here, you're basically saying that a ring morphism is just basically a function that takes a ring of one set to a ring of another set. Is that what it is?
So it maps. Yes. So a ring is a set with some additional structure. It has a notion of addition and multiplication.
So in this case, it's basically just a function that takes one ring, I guess like one particular ring, and then maps it onto another ring, right?
Yeah, exactly. But you don't want the map to be like completely chaotic. You don't want like 0 to be mapped to 1. You don't want like a complete mess. And why I introduced that here is because I want to show. I want you to check that the map that we define later, that we defined previously, that maps Z to Q, is actually a ring morphisms.
And they teach you this in Intro to Set Theory? I mean, Intro to like proofwriting, or is this like more advanced stuff?
Well, it's kind of part of the. Okay. Here I have to like clarify a little bit. There's a few things why I want to check that. Okay.
Yeah.
Okay. The first reason is. The first reason is that first of all, our map that maps Z to Q.
Yeah.
I mean, it's kind of a nice map, right? But we don't know why it's nice, right?
Yeah.
I mean, there is a lot of map that map Z to Q. For example, we can take X and map it to X plus 1 over 1. That would still be a completely valid map that maps Z to Q. So maybe I can write it with a little prime. So maybe it's a map from Z that maps to Q, which is the thing I just said. So we map X to plus 1, right? So why is the first one better map than the second one? Okay. That's like one way to have to answer that. And the reason why the first one is better than the second one is because the first one preserve multiplication and addition. I mean, first of all, maybe like, I mean, here we're kind of building the rational number. You see, we kind of writing like definition out and like, you see, sometimes like I'm asking you what should be the definition of addition, right?
Yeah.
I mean, technically, there's no right answer, right? You could put like some junk on the definition, and if it works, then it works, right?
Yeah.
But it's not what we want. We want like a definition of addition that like works the way we know it, the way we know like it should works, right?
Yeah.
We just like kind of build so we know what a rational number is like from intuition and like from working with them when we do computation, but we don't know what they're them like formally, right? But we sort of know what they are, so we kind of just like trying to take what we know and trying to write like as a coherent like formal theory.
Yeah.
Like we just did.
Oh, okay.
And another way because I like this thing we like to check this definition is because in fact you see this map that maps X to X over 1.
Yeah.
If we put like a reasonable ring structure on Q. So it means like defining addition and multiplication in such a way that this map is a ring morphisms. It will basically impose the definition we wrote before.
Oh, okay.
So you kind of see sometimes like the definition of addition of two fractions is kind of weird, right?
Yeah.
And the reason why it's weird is because, I mean. You usually you have to think about this way. First, you add the integers.
Yeah.
Okay. And then you added like some new number that allow you to talk about like division. And you already had like a notion of addition and multiplication over Z. And all you care about now on Q is to have like a definition which is compatible with the previous one you had.
Right.
And it turns out that this is exactly the definition we wrote before. Like it follows from the one we had on Z.
Oh, okay.
Like for example.
Yeah.
So for example, I mean, when you're like in elementary school, you say, why is adding like two fractions like such a pain in the butt? Like why can I just do like A1's time A1 plus B1 is equal to A2 plus B2 be like just like multiplication? Why is not like something like that?
Yeah.
Right. But if this map is a ring morphism, you get the answer Y.
Oh, okay.
Because look what would happen. So if we look at this map, we get A1 over 1 and we get A2 over 1, right?
It would literally be just like, if you did it the way that you wrote it, it would be like A1 plus A2 and then just 2 underneath. And then you're like wondering why is it that it's cut in half.
Yeah. Which is definitely not equal to A1 plus... I mean, what it should be, right?
Yeah.
So that's the reason why we have like such a complicated... I mean, such a messy definition for addition. It's basically not because... Yeah. It's basically not because we care about defining addition over Q, like we didn't like... what's a good way to make like people suffer, like writing like a definition like that? We just said, well, we had something that works over Q, over Z, and we want to pull it back to Q.
Right.
And basically that's where this definition comes from.
Okay, and I think we can end it right there. Sascha, do you have anything to say to our global audience before we depart for today's stream?
So next time we're gonna talk about so there's two missing structures that we're missing. So we kind of did the arithmetic part. We did like talk about addition and multiplication. No, that's good. And as an exercise, so you will have to check that you get indeed a field.
Yeah.
What we haven't talked about is absolute value and inequality over Q.
Mm-hmm.
And when we have those, we will be able to define what it means for two rational numbers to be close to each other.
Okay.
Like a distance.
Oh, okay.
And this will lead us to talk about sequences and Cauchy sequences, which will ultimately show us the flaw of Q.
So tomorrow we're gonna go over absolute values and distances, right?
Yeah. And if we have time, we might introduce Cauchy sequences and the convergence of sequence.
Okay, yeah, the infamous Cauchy sequence.
Yeah. And I want you to think about it. So in our logical progression right now, so we started with the natural number, was like kind of like the first thing. I mean, literally like an axiom in set theory to have a natural number.
Yeah.
So I mean, those are usually the most intuitive number. Mm-hmm. And then we kind of introduced the integers because we wanted to be able to undo the addition.
Right.
And we kind of went from the integers to the rational because we wanted to be able to undo multiplication. We added like multiplicative inverse. Okay.
Right.
And now we basically have all we can basically undo all the basic arithmetic thing that we know. Mm-hmm. I mean, the basic one. Mm-hmm. But you will see that we're still lacking there's still some issue with Q.
Yeah.
You will see there's like some missing points. For example, we can write like an equation inside of Q, which is like perfectly fine. For example, the equation x squared is equal to 2. Mm-hmm. But this thing will not have solution inside of Q.
Yeah.
And even though it's going to be way worse than that, next time we're going to show that actually a solution to this guy can be approximately at basically arbitrary precision by a sequence of rational number.
Yeah, I'm familiar with this proof. Like, you see it all the time, like, I think in intro to analysis books.
Yeah. And basically this will lead us to the fact that we're missing points. Like, I mean, the fact that we're able to approximate like the solution to this equation by a sequence of rational number is kind of telling us, oh, we should be able to take the limit of this sequence, right, and get some kind of number. Mm-hmm. But unfortunately, this is not the case inside of Q, so we would like to add those points, and basically those points will be the real numbers. Mm-hmm. Okay. For example, in that case, it would be the square root of 2. Yeah.
Oh, okay. And thank you for the follow, Marco 2609. Much appreciated. So that's basically what we're gonna do tomorrow, guys. Just basically go over absolute values, distances, and hopefully we'll get into sequences at that point.
Yeah.
So, thank you, Sascha, once again for giving us an awesome lecture.
No problem.
Definitely learned a lot. So I think like the one question I wanted to ask you before we end stream is that when you were introducing the rings and morphism and fields, I never knew that that was actually in an intro to proofs course. Is that, or is that you just wanted to put that in to basically enlighten us more on the structure of the numbers that we're so used to?
Yeah, I wanted to add a little bit more structure because
Oh,
otherwise we would have like the real numbers, but they would like be like, I mean, we wouldn't have like a good way to talk about to compare, like, for example, addition in Q and addition like in the real numbers, or
like we would lack details, like an explanation on why they're structured like that.
Because at the end of the day, I mean, R is a very complicated thing. I mean, it's not just a set. It has like a metric ton of structure you can put on it. If I would like to like give you like what the structure it has on R, if I just think on top of my head, I would say, well, it's a commutative field which is totally ordered. Which is also a commutative Lie group, which is also a complete Hilbert space.
Like any person that's learning that for the first time, they're like, what?
I mean, there's also it has the structure of a vector space, topological vector space, even though.
And they say they say mathematicians make things complicated.
It adds a lot of things, and what is cool when you do like abstract theory, like ring, is that basically when you think about like an abstract ring, those things has none of that. They don't have like topology. They don't have like Lie group structure or whatever. They don't have vector space structure. They just have like structure of a ring, so addition and multiplication. So you kind of get rid of all the distractions. See?
Yeah. I see that. Yeah, because like because I think like they don't cover this stuff in the course because like in a intro to proof course, I mean, but I'm guessing like you cover rings and fields like in abstract algebra.
Yeah.
So I think that's really cool that you're actually introducing us to concepts that are like in like something that we're not. I wouldn't say we're not ready for, but like I think a portion that's like, oh, we're actually learning something that's a little bit more advanced than what you would cover in a normal course. So I really appreciate your amount of detail into that.
And also I kind of cheated because I need the definition of a field to define what is a vector space.
So I think the question I will like ask you, like the last one, is the difference between a ring and a field. So what I understand what you taught us is that a ring is basically a set that has multiplication and addition, right? So a field, it's like a ring, but there's an extra property to it.
Yeah, it's a ring with more properties. So it's just a ring with more stuff.
Oh, more stuff. Okay.
Yeah, it's basically like there's human and there's like rich human. I mean, a field is a rich human, so it's still a human at the end, but it has more stuff.
Oh, okay, gotcha. Okay, so hopefully you guys can join us for the next lecture tomorrow. For those who followed, Aspire90, thank you for the follow. Marco 2609, thank you for the follow. Like I just shortened the number just so that I can read it easier. But if you guys are curious about math, physics, as well as just like probably have a productive stream in the background, you can always tune into the stream and like drop a follow if you like, if you're watching this on Twitch. But if you're watching this on YouTube, like, comment, subscribe, and probably you can give us more knowledge in the comments down below if you're watching this on YouTube. For my Twitch viewers, I will put out the Discord so you can interact with me, Sascha, and the rest of the Discord community there. I will also put my YouTube link in the chat so you guys can subscribe to my YouTube channel if you would like. And if you want to check out my video game channel, Sascha sometimes drops in there too, so sometimes he ends up talking to me about math there too. If you want to check out my video game channel, my Uncle Talks channel, that's also available for you guys to check out. Alright, so first of all, Sascha, I will say goodbye to you, and I will definitely do more research on rings and fields before our next lecture.
Yeah.
So take care, man.
Yeah.
Alright, guys. So I will definitely upload this on YouTube, and I'm definitely recording these lectures like as we go. So apologies for any like internet cottages. Like, I try not to upload the VODs if it has too many internet cuts, but at the same time, like if the cuts are like not at crucial moments, I will try. If it's at crucial moments, I will try to like upload the recording, because since my internet's the best, it will take the upload a lot longer. So that's why I like uploading from Twitch directly. So thank you for joining me today, guys, and joining us actually. So I just want to say the final thing for today. Always remember, everyone is precious. You guys are just as precious as everyone else, and I will see you guys in the next video or stream. So take care, guys. Bye bye.